Solubility is something that we've kind of talked about in terms of your project. But what solubility is, it's dependent upon two components. You have a solute and a solvent. A solute is the substance that's dissolved in another substance. So often this is a solid. If you're making a solution of something, so let's say you had some sodium chloride. Sodium chloride would be the solute of your salt water, so it's usually a solid. It's often what's added in a smaller amount. So the solvent is the substance that usually a liquid dissolves another substance. So this is the substance that's present in a larger amount if it's not a liquid. Remember, we call water the universal solvent. So quite often for us, we're going to be using water as a solvent. You can use other liquids. You could use ethanol. You could use other alcohols. You could use any liquid. Just we often use water. So what solubility is it's the property of a solid, liquid, or gaseous chemical substance to form a homogeneous solution of the solute and the solvent. So in other words, what it is if you add these two substances together, do they mix and form one thing and you can't differentiate the components, or do they separate? So if something ends up being soluble, that means the substance has dissolved in the substance. So salt water would be an example of a soluble substance. So when you form salt water, you can't distinguish by looking at it that there's the salt dissolved in the substance. You could if you tasted it, but we don't taste things in lab. But there's other chemical tests that you could do as well in order to determine what's dissolved in a substance. Something that is insoluble means that it cannot dissolve. So what this means is when you add the substance to your solvent, it doesn't dissolve. So you can still see the substance. So an example that you've seen before is if you have sand and water together. The sand is never going to dissolve in the water, regardless of how hard you stir it or how long you leave it in the water. It's not going to dissolve. So that's an example of something that's insoluble. So another way of saying insoluble, the solid isn't going to dissolve at all. So we have the general solubility information for most chemical substances organized into this chart. This chart allows us to determine if something is soluble or insoluble. Now, for our purposes, you do not need to have this chart memorized. Anytime you need to use this chart, you will be provided with it. Keep in mind on a quiz or a test that uses this, it may look a little bit different, but it still will have the same information. So we said sodium chloride was a soluble substance. So we can double check that by finding sodium and chloride and see that when the two boxes combine, we end up with in the soluble box. So when something is soluble, that means that you're forming a solution. Insoluble means the solution is not forming. So you end up either with a cloudy substance or you end up with the solid just kind of sitting on the bottom. But just to reiterate, this chart is not a chart you need to memorize. You just need to know how to use it. If you go on to take AP chemistry, you will need to have some solubility things memorized, but we don't need to worry about that right now. So here's a list of 8 substances. What I would like for you to do is first write the formula and then determine if it is a soluble or an insoluble substance based on the chart on the previous page. So I wrote the formulas out for us just so you can double check. What you're going to do is you're going to determine if they're soluble by looking at the next page or the previous page. So we have sodium and acetate. Sodium is right here in group 1. Acetate is right here. So both of these line up to make a soluble substance. So we know it is soluble. A soluble substance makes a solution. so we would write an AQ next to it. So if we were to take the sodium acetate, dissolve it in water, it would make a clear solution. We wouldn't be able to tell that it was dissolved in it. Silver chloride, let's find that one. Use the highlighter function. Silver is right here. Chloride is right here. It forms an insoluble substance. So this is the opposite. So this is insoluble, meaning that the silver chloride is a solid. So in our experiment that we just completed, this was one of the things that you could form with your test. We're eventually going to talk about reactions with this, just not right yet. Ammonium nitrate is going to be soluble, meaning it's aqueous. Calcium sulfate. So calcium sulfate is insoluble, meaning it forms a solid in the solution. Try the remaining few on your own. So here we have it. Again, anytime something is insoluble, it means you have a solid. In this, soluble indicates you have a solution, which is an aqueous substance. Notice the example with iron. There wasn't iron specifically listed in the chart. It was under other. Other sometimes other will include anything that's not listed in any other location. So iron is one of the things that we include there. The next thing we're going to talk about are types of chemical reactions. Below here, there's a lot of different types of reactions that we're not going to talk about in this course. I just wanted you to kind of have an idea that there are patterns here in chemical reactions, and just to note that these are available. If you go on to take a P-Chem, these reactions would be something you would be able to need to know. We're going to talk about 5 types of reactions today. There is a 6th type, but we're not going to talk about it for a few more units. So the first type we have is synthesis. Synthesis is when we have 2 or more atoms or compounds combining to form one compound. Now, for all chemical reactions, we like to classify them as endothermic or exothermic. For us, for right now, all of these reaction types, sometimes they're one and sometimes they're the other. So this one, we say usually it releases energy, which would indicate it was exothermic. That doesn't mean 100% of the time it's exothermic. It's just something to keep in mind. Notice here we have the first reaction here. We have iron, which is an element, plus oxygen, which is an element to make iron 3 oxide. So you can have atoms here. You can also have compounds. In the second example, you have 2 basic compounds, and you end up making a more complex substance. Synthesis, the way I remember this, I think of synthesizing DNA, where you take a lot of small components making one large component, which is what a synthesis reaction is. So you could have 2 or more, sometimes I've seen up to 4 or 5 things in the reactant side to make one product. That's what makes this a synthesis reaction. The next one is kind of the opposite. So we have a synthesis versus a decomposition. A decomposition is breaking apart a single compound. So a single compound breaks into 2 or more elements or smaller compounds. Often this requires an energy source to start the reaction. Energy sources can be heat, light, or electricity. There also can be catalysts used here. But this is usually an endothermic process. Decomposition, the way I remember it, is I think of leaves in a forest. When the leaf falls off the tree, it falls to the ground and it breaks apart into its compounds that made it. So it's breaking apart into multiple things. So in all of these examples, you have one thing becoming at least 2. Again, you can have more than just 2. It's just at least 2. So that's how I identify it. So the decomposition versus synthesis, they are opposite reactions. The next type of reaction is referred to as a single replacement. So a single replacement, what you're going to have, there's two options. You can have a metal replace a less active metal in an ionic compound, or a nonmetal will replace a less active nonmetal. So in this example, we have calcium. Calcium's in its elemental form. It's going to replace the metal in the ionic compound. So if you have a metal by itself, it's going to replace the metal component. So it becomes calcium carbonate plus sodium. Now, there is another type. You could have fluorine gas. Let's say we have calcium chloride. The fluorine then, since fluorine is a nonmetal, it's going to replace the chlorine, so you're going to get calcium fluoride plus chlorine gas. So this is the opposite. So you have to identify your substance as either metal or nonmetal, and then it's going to replace that component. So you can kind of identify a single replacement reaction, because you're always going to have someone or an element in its elemental form. So it's going to be by itself. So in this case, we have calcium and sodium. Something's going to be by itself on both sides of the reaction. So even though there's two fluorines and two chlorines because of the diatomic rules, they're still technically in their elemental form by themselves. A double replacement reaction is when the metals in the ionic compounds switch places. So there's a couple different ways you can think about this. Again, the metal has to be with a nonmetal, because these are always going to be ionic substances. So you can kind of think of it as the first and the last, and then the middle. So if you're thinking of algebra FOIL, so the first and the last go together, and then the middle go together. Notice again how we always write the metal first. So you can do it that way. You can switch the two metals. Just don't switch everything, because then everything gets kind of messed up. So double replacement. Notice there's nothing in its elemental form. Nothing is alone. The last type of reaction that we're going to take a look at today is a combustion reaction, and this is when we have an organic compound containing carbon, hydrogen, and sometimes oxygen, reacting with oxygen gas to form carbon dioxide and water. So if you think, it's usually exothermic. So a combustion reaction, these happen all around us. If you have a car that uses gasoline or diesel, it uses a combustion reaction. So I have CXHY just to indicate this could be any organic substance. It could be gasoline. It could be some sort of oil or any sort of organic substance reacting with oxygen to produce carbon dioxide and water. So this is just kind of one example of that. So if you have a fireplace, that's another example of combustion when you're burning the wood in your fireplace. Now there's actually two types. There's something called complete combustion and in incomplete combustion you only form water and carbon dioxide as your products. So it might be weird to think about water. Notice how water has a G next to it indicating that it's a gas, so that's going to be water vapor. Water is actually produced in fire. It's just you're not making a large amount of it. It's not enough to put the fire out. You would need a larger amount for that. But complete combustion, you only have those two forms. If you have a wood burning fireplace, one of the things that you make is some ash that's left over after you burn all of the wood. So that ash, that would be an example of incomplete combustion, because that's not carbon dioxide and water that's formed. Sometimes you can form other things like carbon monoxide. If you have, you might have a carbon monoxide detector in your house. It's very poisonous, gas. So that would be another example of something that would be incomplete combustion. So incomplete combustion form something in addition to carbon dioxide and water, such as carbon monoxide could form some other substance that would be formed. So what I would like for you to do is I would like for you to write out the chemical reaction for letter A, balance it, and then write the type of your reaction in letter B. So propane is C3H8 to help you out with that one. So here you can see numbers 1, 2, and 3. Number 1 is a synthesis reaction. You have two components becoming one. You don't need the parentheses there. It is a synthesis. The second one is a combustion reaction. You have propane reacting with oxygen to make carbon dioxide and water, making it combustion. And then the third one is single replacement. You have bromine and iodine by itself. So those make it a single replacement reaction. I forgot to include the 4 in the iron for the first one, so there's a 4 in the front here, and it's Fe2O3. So in number 4 you have hydrogen peroxide, which is H2O2. So this is a decomposition. You start with one thing and you end up with 2. Oxygen is part of Brinkelhoff. It's a diatomic, so you need to have it paired. 5, you have another example of a synthesis. You have 2 things becoming one thing, and then the last is a double replacement. So the thing that makes double replacements tricky sometimes is you still have to balance your ionic substances. So iron, it's iron 3 to start with, and it's still iron 3. So you have to sometimes, when you balance it, it makes it a little bit trickier.